Okay, so we are learning about the transformer nowadays. Okay, so last time we learned about this, say, this figure. Okay, so the transformer is consists of encoder and decoder architecture. Okay, so anyways, nowadays the famous architectures like GPT, BRT, that language models are using these transformers as the base block. Okay, so ChatGPT is the application. That is applied to GPT, which is the generative pre-trained transformers. So we will also learn about this maybe two lectures later. Okay, anyways, um, yeah. Before that, I have to maybe notice these things. So today we will finish learning about transformer, and maybe spanning two lectures, we will learn about the efficient object detector. So efficient object detector. So this will cover how to implement YOLO version 2, 3, and also I will also introduce some DETR architecture. We will learn about this DETR today, which is the object detection pipeline based on the transformer. But I will introduce RT-DETR, which means real-time DETR, which is producing the real-time speed. Okay, next classes, we will learn about that. And then next class will be about the vision language signals. So nowadays, because this course, we are learning about the computer vision class, which deals with images and videos. So we are learning about how to process the image or video signals using the deep learning architecture. But language words is, nowadays very becoming popular, right? So there's some, deep learning and AI models that can simultaneously tackle vision and language signals. So we will learn about very basics about that. So um, there are some algorithm called as CLIP. This is also introduced by OpenAI. So we will learn about that. Starting from this clip, we will learn about a few vision language models, okay, and spanning two classes, okay. Uh, and also this day, I will also cover some optimization techniques, which is slightly different from the uh, stochastic gradient descent we have learned. So we will learn about Adam and other types of optimizer, which is slightly advanced compared to the gradient descent. So in the last lecture, we will learn about that. And this day, there will be no official lecture, but I will proceed the Q&A session, okay? And I don't know, maybe December 2nd, we will have quiz 2, okay? And this is the last lecture, okay? And then also maybe around, maybe next week, we will also raise the assignment 2, okay? And that deadline will be 1 month later, okay? So mid of December will be the deadline for this. So this is the remaining schedule, okay? Okay, so this is the, anyways, this lecture today, we will also learn about transformer-based vision techniques, okay? So starting from LSTM, we learned about the transformer in NLP domain in previous lecture. And I also told that this figure is same as this. Okay, are you guys understanding this? Right? Okay. And but one more thing remained to properly understand the transformer. Okay, so as I told you, the input of the transformer are transformed to key query values, okay, by applying some linear, how to say, matrix to be multiplied. And actually that matrix is parameters of the transformer. We are transforming our input to key query values. And this is the attention mechanism. So we are dot producting the key and queries, and using that as the weight, we multiply the value, okay, to get the feature. So somehow in attention mechanism, we are finding the weight between the pairwise samples and getting to get the feature for some query. We want to get their, pairwise, features. So with this weight, okay. So that's the attention mechanism. But this is attention using just one stream. But normally we are using multi-head attention. So multi-head attention means there are multiple head for this attention mechanism. Okay. So this is, making the attention, their responses more robust, okay, by giving some randomness. So getting multiple key query value, their attention result, we are actually concatenating them and also multiply one more weight, which is the output weight, okay? So getting some randomized, attentions, and by concatenating their, result, and multiply one more weight, which will be learned by ourselves to get the final result. So this is the multi-head attention mechanism, and it is known to be more robust than just having just one head. Okay, normally we are using 4 to 8 multiple head, okay? So to make the overall responses to be more robust, okay? And it is visualized like this. So value key query, this is the visualizing one attention mechanism. So we are applying the matrix multiplication between key and query, and apply the softmax and also multiply with value. So this is the one attention, and we are applying multiple attention mechanism and concatenating them and having just one more weight, okay, to get the multi-head attention mechanism. So this is the core operation of the transformer, okay, the attention. And transformer, so this is non-sequential operation. So encoder side, still the decoder is operating as the sequential manner, but encoder, when operating the encoder, every tokens are already available when calculating the self-attention mechanism. So I am a student. This whole sentence had to be available when calculating attention. Okay, are you guys following this? But when constituting this with, when constituting the encoder with the LSTM sequentially getting each word and propagate their intermediate features to the next token. Okay, are you guys following this? So in that sense, transformer, we call that as non-sequential, but LSTM that as the sequential. So thanks to this characteristic, the transformer, their features is becoming more robust, okay? Because they are, considering all the world parallelly, and at the same time, because of that, there's no risk to lose the past information. LSTM by nature, even they improve the RNN using the adaptive learning schemes to how to forget and how to retain the information. Thanks to that module, LSTM is losing less information compared to the RNN, but transformer, all the tokens are already available, so there's no risk to lose the past information. Okay, that is the merit of transformer. At the same time, they allow parallel processing. Okay, so because all the tokens are already available, we can apply, different thread to calculate each pairwise calculation, okay, simultaneously. So we can make this all overall process parallelized and to be efficient, okay? So that's the merit of transformer. So, in both speed and also in the accuracy, the transformer has some strengths compared to the LSTM-based alternative, okay? And this is the first architecture that is proposed for the vision domain. Okay. And the CNN, you may remember that CNN architecture that is first introduced in NIPS 2012. And after that, AlexNet and BridgeNet, Google LUNet, and ResNet, they appeared. And after that, after ResNet appeared, most of the architectures are composed of the ResNet. Okay. But in 2020, and maybe to 2021, this trend, use of the ResNet has been gradually replaced by this Vision transformer nowadays. So actually, this is very important architecture, but it is very simple to understand actually. And also one thing you have to note here is they are using only the encoder, not decoder. Okay, they are not having the decoder. Because the image features, we are already having all the tokens. We are already securing all the image information because image data is not sequential, but the word data, they are sequential, okay? But image, how to say, data, they are not sequence data. So there's no serious reason to use the decoder as well. So they only provide the transformer encoder as the feature extractor for the image domain. And their architecture is quite simple. So their paper name is like this. An image is worth 16 by 16 words. Okay. So this means they are dividing the overall images into some patches with this size, with this size. Okay. So they are dividing all images into 16 by 16 patches, and then they are inputting this as the input token to the transformers encoder. Okay, that is the main idea of the vision transformer. It is quite simple. And also here, the objective of the vision transformer is for doing the image classification. Okay, so image classification, we just estimate one probability vector for the whole image. Okay, this is the most, simplest form of the vision application. And they are first, divide the whole image into several patches and then apply the linear projection, which is applying the linear matrix multiplication to transform each patches, okay, as the feature. Okay, and then they apply the positional encoding in 2D space. Okay, So similar to the positional encoding vector in the world. So previously I mentioned that the transformer, they cannot encode the order of the tokens. So this type of positional encoding have to be added in the for the input, okay, input tokens. And this was the one-dimensional positional embedding because the words, they are in the one-dimensional space. But these tokens are in the two-dimensional space, right? Especially they are in the 2D space. So their positional encoding have to be in the 2D space, okay? So anyways, the two-dimensional positional encoding have to be added to the patch features, okay? And then they are inputted to the transformer encoder and also have one classification token. So we call this as classification token, okay? We call this extra token as the classification token. So we then apply the self-attention mechanism on these, how to say, input tokens, which is coming from the image patches with the added with positional encoding with the classification token to output the improved features. So here as well, we are getting the improved response, okay? By applying the attention mechanism between these, we are getting anyways the response from these tokens as well. But we will use only these tokens result, which is improved via this attention mechanism. And we are actually applying few more MLP layers on this token result and map it to the classification probability. Okay, are you guys understanding this? Okay. So, I mean, this is another, figure that is visualizing this. So this is the embedded patches, and we are actually, apply some normalization. How to say this is operation is also some differentiable operation. Anyways, we are converting these image tokens into p-query values and apply the multi-head attention and map it to the class probability anyway. So the one output of this transformer encoder is mapped to via MLP to the class probability. That's the vision transformer. Okay. So this architecture is very simple, having only transformer encoder applying just one attention mechanism. So there's no cross attention. There is no cross attention. So I already explained this. So this is called as cross attention because key query values are coming from different sources. But transformer encoder, it is only having this self-attention mechanism whose key query values are coming from the same signal. Okay, cross attention that is applied by making two input from the encoder's output and one input from the decoder input size. Okay, but in the transformer, vision transformer, there is no operation like this because there is no need to mix the image features to make the final output, but they just output class probability using only this encoder architecture. Okay, that's the vision transformer. Because this image classification is quite simple, so they don't need complex architecture, but getting good result compared to the state-of-the-art CNN-based architectures. Okay, so this vision transformer, they are replacing the CNN-based baselines. So this is showing the exact, formulation, operation inside the vision transformer, but they are actually sequentially applying this type of operation. I mean, that is constituting the transformer encoder. So applying the self-attention and applying MLP multiple times. Okay, basically what they are doing is this. Okay. But next thing we have to learn is DTR. So this is a more complex architecture, and actually this was appeared ahead, I mean slightly ahead of the Vision transformer. So this is the transformer-based architecture for object detection application. So this is more complex and having both encoder and decoder architectures. But in VIT, it only has encoder and it appeared in actually 2021, and it is aiming to achieve image classification, which is simpler than object detection. Okay, and this is the architecture of the DETR. Okay, from the image, what they do is rather than using the 16 by 16 patches in DETR, they are first extract the image features using the ResNet. So they are actually using the state-of-the-art image feature extractor. And then they apply transformers encoder-decoder architecture by regarding each dimension of ResNet as the input token. Okay, so I mean in VIT, the input token was the image themselves. Their patches are used as the input token to the Vision transformer. But DTR, they are using the element of image feature. This will produce like this dimensional image feature, and their element is regarded as the input token in transformers. And actually, their input tokens as you know already know, their input tokens are inputted and they are outputted via self-attention and cross-attention mechanism. And these output are further mapped to, by applying MLPs, they are further mapped to the image location, which is a bounding box location, and also the class probability. So each tokens here is mapped to one bounding box and class probability estimations. Okay, so and by doing that, this DETR can estimate this type of output. Okay, but I mean you already remember that YOLO, they are producing very many output first, which is the bounding box and classification result. From YOLO, there are many outputs are estimated, and by applying non-maximal suppression algorithm, we filter out unnecessary output. That's the way this YOLO worked. Okay, but in DTR, they are not using NMS. Okay? And they are saying that without using NMS, the transformer-based architecture, they can produce very good accuracy. Okay? So that's the merit of this DTR. Their accuracy, even without NMS, their accuracy is very good. Okay? And compared to the two-stage methods like faster RCNN, this DTR is also having very good performance. So it is proving that transformer-based baselines, they are producing good accuracy. Okay, so it is also meaning that transformer, it can be a good backbone architecture, even for the vision application. I mean, not merely to the NLP domain, the transformer, that is a very good backbone architecture for the vision application as well. Okay. So I will explain more about this DTR architecture. giving some to give some intuition to you maybe. So, but you don't have to implement this DETR in your assignment. Okay, don't worry about that. This is very complicated architecture to implement, so you don't have to implement that. But maybe given some implementation, I think you can use PyTorch to train this DETR because the training code is already available. Yeah, but I mean, to use that, you also have to roughly understand how they work. So I will, I want to anyways give you some intuition of this DTR implementation. So in the backbone, as I told you, they are applying ResNet architecture. They are applying the CNN-based, state-of-the-art CNN-based image feature extractor to the images and extract some feature. And then also apply the positional encoding. And they use this element of the image feature as the input token. And by adding them with the positional encoding, so this input token to the transformer encoder is coming from the image features rather than the patches, differently to the VIT. And encoder, they are first apply the self-attention between the patches, okay? And then improve the image features once, okay? So encoder in the transformer, they are doing feature improvement, okay? So encoder of transformer, they are normally does the feature improvement. So here, this is the transformer for the NLP. So this is the input. And by applying self-attention, they are getting some image feature here. Not image feature. They are anyways having some features here. And this is the decoder input. And here, via the cross-attention mechanism, they are somehow mixing the improved feature with the decoder input and getting the decoder final output. So that's how this transformer is working. Okay. So somehow the role of the encoder of the transformer is improving the initial feature. Okay. So here we already have some feature, but via this encoder, we are somehow improving those features and use that to mix it with the decoder input. So that's the concept of transformer. So here we can interpret this as similar to that. So encoder, we already have CNN-based image features here, okay? But we are improving that using the transformer's self-attention mechanism, okay? Are you guys following this? Okay. So here we are getting improved features, okay? And then using the cross attention mechanism and by mixing this improved image feature with the decoder input, we output the final output from the transformer decoder, and that final output will be further mapped to class probability with class and bounding box information via these final NLP layers. Okay, so each output of this decoder is mapped to, this final output, which is bounding box and class probability. Okay, so some output will produce no bounding box because they are saying that there's no object in that position, right? But some are mapped to the object and bounding box locations. Okay, are you guys understanding this? So here I didn't explain about this object queries, which is the input to the transformer decoder. Okay, yet I didn't tell about this yet, but this part is very tricky in image domain. So in previously in NLP domain, this was some French sentence. So here we use this encoder-decoder transformer architecture for translating English word to the French word. And we used this, outputted words as also the input to this decoder input, okay? You may remember this, okay? In NLP domain, we did this kind of things, okay? But in image domain, this is slightly different part in image domain. So our output is not having this type of sequence, okay? In images, we can map all the decoder input to the bounding box or class probability simultaneously, not doing that sequentially as in the NLP domain, okay? That's one difference. And also in our application, these decoder input are not having semantic meaning, okay? Our decoder inputs are not having any not having any sequence, and also at the same time, our decoder inputs are not having semantic information. So in here, in the NLP domain, in translation task, this have to be some French word coming from the previous stage, okay? But in image domain, we don't have such sequential meaning. At the same time, we don't have any, this type of semantic French word in the image domain. So image domain, these object queries are some, random vector, not having any semantic meaning. But during the training, we can update. So, at the initial step of the training, we randomly initialize these object queries as some vector, okay? Randomly initialized vector. But for the training data, we can update these object queries to maximize the training accuracy, okay? Are you guys understanding this? At initial stage, this was randomized, but we can anyways update these object queries to maximize the training, their accuracy, okay? So, but after training, even after training, these object queries are not having any semantic meaning, okay? Are you guys following this? Okay, so these object queries can be updated, but not having any semantic meaning. But still, it can make this object detection work. So we are using that. So, there are some, many questions on the web. Questioning about the meaning of this object query. Indeed, there is not much meaning for these object queries in DETR architecture. So, some subsequent DETR variant, they are giving some spatial information in these object queries because, many researchers are finding that, this DETR training sometimes goes taking much time. So they are pointing out that these object queries, they are not having any semantic meaning. So that is the reason why it takes a lot of time to map these object queries to the bounding box and class information. So some try to improve these object queries by giving some spatial information. And indeed, it can accelerate the training of the DETR. And that kind of work is conditional DETR or spatial DETR, and many works are proposed in ICLR or other top conferences to improve these object queries of the DETR to give some spatial information. And indeed, they are improved, but we are discussing about this DETR. And at initial DETR, because of the difference between NLP domain and vision domain, these object queries are not having much information in vision. Okay? And also transformer decoder in NLP, they are somehow sequentially operated. So at the first time, they are having only this. And using this as the additional input, they do this, okay, in NLP domain. They did this decoder part sequentially, right? Gradually having more decoder input. But in image domain, we don't have to do that because our output is not having any sequential meaning. Okay, so we are getting all the object queries one time, and then mix it with the image feature and estimate that and map it to bounding box information. Are you guys following this? Okay, yeah. And another important thing is object queries. They normally have 200 to, anyways, their number is initialized to this because they are mapped to one bounding box and class probability at the final output. So, if one image is having more than this number of objects inside, we cannot uh, estimate more than this number of objects. So, in detail, object query numbers are normally set as this by assuming that there would be not much images in the real world having more than this number of objects inside. Okay, but maybe if depending on the application, we have to change the object query numbers, right? Definitely. So are you guys following this? And DETR, this is the original transformer architecture that works sequentially, but this is the figure drawn in the ECCB 2020, which is which draws the pipeline for the DETR. So previously, the input was a word sequence in original transformer, but we are starting from the image features extracted by the ResNet. Okay, so their input is now ResNet, and we are applying some spatial, the 2D positional encoding to these two key inquiry and not for value, and apply the multi-head attention. And anyways, by sequentially applying normalization and FFN, which is the MLP, we are improving the CNN features. Okay, this is the improved feature, and they are actually, going to value and key for the decoder, their cross attention mechanism. And here, the object queries are some randomized vector, but they are updated during the training to maximize the training accuracy. Anyways, this is some vector which does not have any semantic meaning. Okay, but they can help us to improve the overall accuracy. Anyways, they are inputted to the object decoder and applied with some self-attention first to slightly improve it, and then applied with cross-attention to mix the decoder, their input, with the improved image feature, and to map it to bounding box and class information. Okay, and also we have to set the number of object queries to 200 to 300 to estimate that number of bounding boxes and class probability for an image. Okay. Are you guys following this? Okay. So this is the DTR and also decoder. There was some semantic operation, and we call that as auto-regressive manner. The output of decoder is again feed to the input of the decoder and apply another stream of self-attention. That is applicable to the NLP domain, but decoder, that is one pass done in the image domain. Okay, that's big difference. But this is maybe also the other difference to the original transformer in the vision domain. So here in the original paper, ECCB, this paper is, I mean, I mean, proposing this DTR, and DTR is actually, the name comes from detection transformer, okay? They are focusing on the object detection task, so DTR is detection transformer, okay? And when applying because I mean, in object detection task, the situation is like this. So, I mean, this is visualizing the final transformer's output response. So, I mean, in DTR, from the object queries, which would have this number of object queries, okay? Using the decoder of the transformer, they are mapping it to class probability and bounding box information. So for each object queries, they are mapped to this each number of bounding box and class probability. Okay, so we call that a set of box predictions. Okay, and this is visualizing this information. So, and this is visualizing the ground truth. Okay, so ground truth image, it have only two object inside, but because we are having this amount of object queries, okay, as the input to the decoder of the transformer, we are actually estimating the same number of output, but most of them will map to no object. Okay, so here in detail, we are not using any NMS, which filter out unnecessary bounding box, but I mean, they are I mean, using all the information without all the output without applying NMS. But most of them should be mapped to no object, but there may have this kind of wrong predictions. There should be this kind of wrong predictions. So for example, here, the green box, that is denoting some object, but indeed, in ground truth, there is no box like this. So this box have to be mapped to no object, okay? And only these predictions should be mapped to the this part, okay? Their corresponding box ground truth, they have to be mapped, okay? But I mean, when given only these two sets, there's no, I mean, mapping these two here and these two here and these two no object is non-trivial to achieve when given this set of predictions and set of ground truths. Mapping this is sometimes non-trivial. So actually mapping that part is here. So what they do is this sigma n means this type of all the permutations. I mean, um, this is sometimes non-trivial to understand. So this is the set of prediction, and when visualizing in the image space, we humans can certainly see this should be mapped to here, and this should be mapped to here, and this should be mapped to no object, okay? But before visualizing in the image space, given only this, sometimes it is hard to map to their ground truth. So ground truth having only this box, and I visualize that with this, and all the other have to be no object. Okay, this is the ground truth set, right? Are you guys following this? Okay, and this is how to say the predicted predictions. Okay, but there's no spatial meaning in this prediction. So what we do is we permutate the order of these predictions this amount of time. So if there are n number of predictions, there are n factorial permutations like this. Are you guys following this? And among that permutation, we have to select one best permutation that is matched with ground truth. Are you guys following this? Okay. So this formulation is showing that. So this loss function, this objective is saying that this is the probability mapping, and this is the bounding box mapping. So this is the ground truth. Sorry. Again, this is ground truth and this is prediction. So they are somehow comparing ground truth and prediction and measure their matchiness in the aspect of two things, the probability and bounding boxes. And they are among all the permutation here, they are finding the best permutation that is minimizing this match between ground truth and prediction. Are you guys following this? And they first anyways find the optimal prediction set. So, I mean, there's no order here. The initial prediction, seeing only this, not visualizing that in the image space, we cannot match this response to ground truth well. Okay, so in this first step, we are permutating this initial response and make n factorial. If the number of predictions are n, then we permutate that prediction n factorial times. And among them, we find the best, order of the prediction that to match it to the ground truth. Okay. Are you guys following this? And then in the second step, what they do is they apply probability laws and bounding box laws on this set. I mean, we find that this is the optimal order of the prediction because, this is matched with this box, and this is also matched with this box, and all the other have to be, matched to the non-object. So this is somehow the best order of prediction. So we are actually applying L2 laws on the bounding box and class probability for each things, okay? And that is, happening in this second stage. So we minimize loss for, this optimal prediction set, which is sector, sigma hat, okay? To close their response further close to the ground truth, okay? Are you guys understanding this? We first choose the best permutation from the prediction and then apply loss function. Okay. So in this way, DETR doesn't have to apply NMS because their output predictions are all matched, well matched to the ground truth. So even they are matched to the no object, so differently to the YOLO, we don't have to further process further filter out those responses. Okay. At first glance, this is not trivial to understand, but I hope you can understand this. This is very easy concept when seeing this figure, right? And result compared to the faster RCNN, which is the, best CNN-based object detector, DETR is producing a very good result. Okay. Okay. Okay, that is the result. Okay. And next week, actually, we will further learn about the RT DTR, which is the real-time DTR. Criticism regarding DTR is even though their performance is very good, their speed is very slow. So I mean, RT-DTR, they are accelerating the implementation of the DTR. So we will learn about that. And also next week, we will also learn about YOLO version 2 and 3, which is a revised version of YOLO version 1. Okay. And now, as I told you, YOLO is having version 12. But I mean, after YOLO version 3, the original author of YOLO is not maintaining YOLO, but third party is maintaining it. So it is a bit hard to search for their technical report, but some versions are publicized. So if you are interested in, you can also explore that afterwards. Okay. But anyways, we will learn about this RTDTR and YOLO version 2 and 3, how they can be implemented. Okay. Thank you for today. And we will finish here for today. Okay. Thank you.